First of all, we will study the which one is there. So let's say we will study first that common emitter or common. Okay, emitter characteristic is there. So we'll study that common emitter. Okay, this one input characteristics and output characteristics. Okay, so in the VLab we will study that common emitter one for these things. Okay, so now if we can see, okay, there is another thing you have to remember. This thing, for operating condition means right now we have studied there are three mode of operation depending on that similar to the two-port model, which one you want to make it as a common to fit it into that two-port model. That is more different mode of operation, but in that particular mode of operation you can have a four operating condition. As you can see, there are two diodes. I already shown you. My screen is visible to you?
Yes, sir. This is
This screen, browser screen, Google Chrome screen, right?
operation of BJT.
Yeah. Okay, yeah, that one. So as you can see here that there are four operating condition as there. So basically three operating modes are there, and in that mode there are four operating condition. So in case of common emitter also, as we are discussing one mode, common emitter mode. So there are four operating condition. In this way, that base collector junction is in either forward or reverse, and the base emitter junction is either forward or reverse. Okay, because as we already, I already shown you that two diodes are there. Two diodes means two junction are there. So let's this is common emitter junction, right? So in this case, common emitter mode. So in this case, base emitter junction, let's say it is, if it is in reverse bias, if it is in reverse bias, and that base emitter junction is also in reverse bias, then the operation mode of the operating condition will say cutoff region, or you can say the transistor is in cutoff region when both of the uh, junctions are in reverse bias. Then you can say they are in cutoff region. If let's say this one is reverse, means base collector junction is reverse, and this one is forward, means base emitter is forward junction, then you can say it is in active region. But which active? Forward active region. Okay, and it is similar for, means if the base collector junction is in forward bias but the base emitter is in reverse bias, then it is in active region but in reverse active region. And if both of them are is in forward region, then it will be saturation region. So what does it mean actually, cutoff, active and saturation? We can I think you have already gone through the characteristics, theoretical characteristics of a transistor, but still we can see that from that lab experiment curve, what is the from the input and output characteristics, if we can see that or we can easily distinguish these three different region. Means not three, these are basically four, you can say, or you can say three region. Means one active region is there, and one cutoff and one saturation region is there. So then you can see what is the difference between these three region. Okay, so these are different operating conditions for a particular configuration. So there are descriptions are there. Cutoff, for cutoff region, I think you are familiar for cutoff region, active region, and also forward active and reverse active and saturation region. Okay, from there you can have a particular uh, limiting condition that you can apply. Let's say you want to operate this transistor configuration in saturation region, then what would be your limiting condition that will help you to achieve that condition? Then you can if you can see from there. Okay, so basically this will be our circuit configuration. So though there are means it is only the transistor connected to the sources, but it is a good habit to apply a resistor through this means with this terminals electrode. Let's say in case of base also we have to apply a resistor. When we will simulate it, we can see, or else from that VLab one also you can see one resistor should be there. It is a good habit because it will minimize the loss of the particular transistor or device. Okay, so in this case, as you can see here, this is our input terminal. So, and this is the emitter one. This is common for input and output. And what we have to measure, this is the VBE, base to emitter potential, and this is VCE, collected to emitter potential, and this is IC, IB, and IT. Okay, this is for output characteristics that we have to measure. Okay, now let's, without wasting time, let's simulate the circuit for input characteristics. Okay, so as you can see, this is the transistor. Oh, okay, could you please tell me which kind of transistor it is, NPN or PNP? What kind of transistor it is? Anyone?
NPN, sir.
NPN. Yeah. Okay. Anyone else? Anyone else? What kind of transistor it is? NPN or PNP?
NPN.
NPN. Okay. So only 2 people are online. Okay. No issue. So this is the NPN configuration, as you can see, and one ammeter is there in order to measure this collector current, and one voltmeter, 2 voltmeter is there. Two voltmeter is there, basically to measure the voltage VB and VCE, and this one is to measure the base current. Okay. So what we have to do in this case, we have to varying this rheostat value, RH1 value, we are able to change the, basically VB means we are able to change the current through this base, or you can say you will change the VBE. So from there we can have the voltage to emitter, base to emitter voltage and base current. So let's increase it one by. Okay, this is for IC and VC changes, as here we have applied. So this is only the biasing part. Okay, so we are not dealing with this one in this case. So we are interested only for input characteristics. We'll have to consider for these things, base emitter voltage and the base current. Let's say for this case, our what is our base emitter, collector emitter voltage, that is 0.1. Okay, let's make it fixed up to 1 volt. Let's say 1 volt. Why I'm doing that one, I will tell you. Means because we have to plot different data characteristics for different set of data, or you can say different set of data for different values of VCB, CE. Though we are using that input characteristics, but still we have to apply. I'll show you. Let's say for this case, we have considered considered that VCE as a 1.1 volt. Okay, So please note down this value VCE as 1.1 volt and then add the table. Okay, it is added already. Okay. So in this case, the base emitter voltage is 0.16 and the base current is 2.51 microampere. Let's increase the voltage. Then voltage across base emitter voltage is 0.36, current is 3.345 microamps. Then again microamps current is there for 0.62 voltage. Now we have applied 1 volt and the current is in 9.092. Still it is in microamps. Now we have applied that 1.48. Then we have applied 1.76 value. And finally that 2 volt. Okay. So you can plot that data. Or else it will be better if you people just, okay, let me copy this one. Okay. I'm copying. Actually, what I am trying to have a several set of data for collector emitter voltage. Now you can see we have this set of data for a collector emitter voltage of 1.1 volt. Now we are going to increase the collector emitter voltage and we will take all all set of data that we have taken already, and then we are trying to measure what will be the characteristics. Then at a glance we want to see the whole picture. That is why we need this one. Let me copy this data. Or else we can have this much for plotting. Okay, no, let it be. Yeah, let me copy this data and then we will have the same experiment with different value of collector emitter voltage. So this is the voltage B E, and this is IB.
So we can see only VLAB screen.
Oh, okay. Thank you. Yeah, now it is visible.
Yes, sir.
This is IB. So this is our base current in microammeter, sorry, is in microammeter, and this is in voltage. Okay, so first of all, let's plot this here. No, okay, one more comment should be there. It is for 1.1 volt of VCE. Yeah, sorry, not VCE. That should be VCE. Okay, so that should be the comment. Then also we will have different set of data, and now we can directly plot it to. Now VLAB screen is visible. No, I think.
No, sir.
No, sir.
Yeah, now it is visible. Okay, okay.
Yes, sir.
Yes,
Yeah.
sir.
So now we can plot it. Then we can have, yes. So this is kind of, you can say that if we go beyond this, then it is kind of the diode characteristics, that forward bias diode characteristics, right? So we have data only from point one, or else if we can have a data, let me try. If we can have a data from further less value, then it will be better. Okay, we'll from the next graph we will try to find that. Okay, now what we'll do, we will have a different set of data for that VCE value of, let's say, 2.5 volt, or okay, that was in 1.1 volt, so let consider it as a 2 volt or 2.1 volt. Okay, it is in 2 volt. Good. So now let's have some data. Now this at this condition, at this data. Okay. Yes, for 0.02, and okay, collector emitter voltage is 2 volt, and this base emitter voltage now we are going to vary. Let's, with smaller step, add all this data. A little better. So you can see that is there any difference or not if we are going to change this collector emitter voltage, and is there will be any change? And how many of you are thinking that there will be change in net? I mean, this graph. Do you think? Are you thinking right now that this will change? Anyone? Are you thinking that this value means this curve will be some sort of different from the previous one? Here you can see it is quite similar. So if we compare with that previous one, it will be similar or not? Means, what do you think?
Yes, sir. Same.
Sir,
I mean, similar.
Similar means there will be no difference, right? Okay, I don't know. Let's check it. Okay, this is for 2 volt. Okay, let's have some other data, then other data value. After that, we can copy it. Yeah. And then we can plot them together. If then we can see is there any changes or not. Okay. Oh, right now you cannot see the data. Okay, just I have copied this data in this format here only. Okay, nothing else I have done. And after all, we will plot them together in one window. Then we will see is there any difference or not. Okay, now let's come here and clear all the data. Then we will consider RH value as a 3 volt. Sorry, not RH value, that collector emitter voltage. Let's have 4 volt. Okay. Oh, it is decreasing. Let's have it as a 4 volt. Okay, this is 4 volt. Now, in similar fashion, what we have to do, we have to vary that voltage across that base emitter junction and add them in the table, and then we will plot. Okay, let me allow for a few moments, then we can have all the data. Then we will see is there any difference or not. Okay. So for these things, we have to do for output characteristics also. I think you are familiar with input and output characteristics of transistor, right? Can you remember the graph? Means what kind of nature it will see, it will be. Can you remember? Okay. For the timing, plot it. Okay. It is showing similar fashion. Okay, now just plot it over here. Delete this one, and we can have a data for. Okay, this was for 4 volt, right? We see for this case it was 4 volt, right?
Yes,
Not
sir.
3 volt. Yeah. If you are online, then you people please respond. Then it will be means at least I can think that okay, you people are here at least. Otherwise, it will seem that I am telling on my own. Okay, you are not able to see my screen.
So we
Yeah.
left also.
Yeah, virtual live viewers. Okay. Okay, for this one it is 4 volt. Okay. Good. Now convert it into X. Okay, we'll have only another one set of data. Let's say 4 volt, and let's have some maximum value for that one. Okay, then only we'll see what will be the effect. Otherwise, we will not have. We are running out of time. Let's clear it. Okay, then extreme value you will take. So okay, 10 volt. Good. Let's have some data for 10 volt. 10 volt for capacitor emitter junction. 10 volt we have applied. Okay. So could you please tell me in which bias is that voltage emitter junction and collector emitter junction are in? Means you have two diodes, right? Or two junctions are there. So could you please tell me from this configuration or from this circuit that in which bias they are in differently? Means two junction. Name it and tell me in which junction, which bias it is in. One by one, you can tell me. Did you get my question?
Repeat once again, sir.
Yeah, the question is that from this circuit, please tell me which junction means there is two junction, right? Bipolar junction, so means two junction is there. So which junction is in which configuration means whether it is which bias basically. So whether it is in forward bias or reverse bias. So and so please tell me for this one and this one.
Base emitter forward bias, collector base reverse bias.
Okay, good. Anyone else? Okay, let's. Anyone
Yes,
else?
base emitter forward bias and the base collector is reverse bias.
Okay, Suraj, you are also with the same answer. Okay, apart from these two, anyone else want to add? Okay, so we have the data. We are with data. Yeah, now there you are absolutely correct because our base is P type. So and you can see positive side is connected to the base directly or through the resistor, whatever you can see. Say now, so that is why it is in forward bias, and collector is N type because it is NPN transistor. But from here you can see it is connected to also the positive side. So N is connected to positive side means it is in reverse bias. Okay, so both of you are correct. Thank you for at least telling this thing. Okay, now what we will do, we will do just the plotting one. Okay, let's delete this data, delete this indexing value and change it to the X. Please don't bother about this plotting thing. Okay, and for this one, this is 10 volt. Okay, so first copy it and write it on 10 volt. 10 volt. Okay. Now all of you are telling me that it will be in same fashion, right? Means there will be no difference. Or those of who are in, all of you are agreeing with that one, that there will be no change or any deviation is there. Someone is telling changes will be there, someone is telling changes will not be there. Okay, please first let me know those who are telling that there will be no changes.
Yes, sir. They will. I think they look similar.
Okay, two of you told me that there will be similar. Anyone?
Yes, sir. I think similar.
Similar. Okay. Someone through chat also trying to convey this. No changes. Jitendra. Okay. So I think 5 people told me that there will be no changes. So okay. Now please tell me those who are telling means thinking that at least there will be changes. Anyone? Those who are thinking at least there will be some changes? No one? Okay. Let's have this plot. Let's plot it. And then, yeah. Okay. So as you can see, almost same nature. They're not different, right? But I think you can remember, means you can recognize this curve with that diode curve, right? That diode characteristics is also something like that. Till up to some voltage, there will be no current, and after that, there will be certain huge amount of current is there. So that is why basically this is also one means input characteristics means basically one diode characteristics you can say. Okay. So is there any query right now or till now what we have discussed? Okay, you people can see my screen, right? The graph you can see. Yes, you can see. Okay. So
Yes, sir.
yeah, do you have any query till now? Okay. I think you don't have. Okay. Now let's do that other one, output characteristics. Okay. So this is the output characteristics for in virtual lab. The same setup is there, but only the changes is there here. We are going to have the collector emitter voltage for with collector current in milliamps. That base, remember the unit also. Base current was unit was in microamps, and in collector output current was in milliamps. Okay, so basically, if you can think that your current is at least scaled up, input current was in that microamps and output current is in milliamps. So which configuration it is? It is in your common emitter. So common emitter is having, which one is there? Common emitter, current gain is maximum or voltage gain is maximum? Can you remember? Okay, no issue. You just go through once that table, then you can, everything will be clear to you. Anyway, okay. So for this time, initially we make this VCE as a fixed, and we are changing these things and measuring the IB. Means we are changing the base emitter voltage and changing measuring the current IB base current. In this case, what will happen? We have to make it fixed, RH as a fixed. Let's say a very small value, 0.12 as a voltage across that base emitter junction, and the corresponding current is very high, means 11.87. Obviously it is in microamps, but still if it is possible for us, no, this is the minimum possibility. Okay, so we have to start with this value. Base emitter one is 10.29 volt, 29 microamps. It will be added here, and we have to note it down. Now what we have to do, we have to change this VC by changing this value. So let's have some VC from some value and add it to the table. So as you can see, base current is 10.29 and collector emitter voltage is 0.8. Okay, can't we have a very less value to that one? Okay, 0.1. Okay, we'll change it again. 0.1, then 0.9, then change the value to 2.2 volt, 3.1 volt, then 4.6 volt. So we have to vary this voltage across the collector emitter junction, and we are measuring that collector current only. Okay. Yeah. So now we can plot it directly, but what we need that variation. Okay, these things, this type of nature. I think you are familiar, right? Initially, when the voltage is increasing, then the current value is increasing. Actually, this extra dot is that due to that we did some mistake. That is why. Otherwise, initially there is increasing nature is there. Then after some certain value, the current is saturated. From table also you can see the current value is constant, 33.01, 33.01 and 33.3. From here you can see, right? Oh, sorry. Okay. So now add all this. Okay, this time how many of you are thinking that there will be no changes and there will be changes? Last time only one, means one-sided, there was no such democratic something like that. But this time, how many of you are thinking that it will change or it will remain constant for different base current?
I think it doesn't change, sir. I think it will look similar. Maybe. I don't know.
Okay.
I mean, shape of the graph will be similar, but the values may be
Mm-hmm. Sorry, I didn't
shape.
get you properly.
The shape of the graph will be similar.
Okay, means like previous one, right?
Yeah, similar to all of.
Okay. So anyone else? Any comment? For this one, IB was 10 microamps. Let it write as IB 10. Okay. Equals to 10. Anyone with any other comment? Okay, let me have some data with different value. Oh, sorry. You cannot see that one, right? Okay, actually, I have just copied the data in graph plotting software, and then we'll have that again, another set of data. Okay. So let's clear all the value. Then initially our IB was 10. Now what do we want? Oh, not this one. Now we want 20. Okay. Okay, let's this value 20.43. Okay. For this one, add this data, then increase this value, and we can have the different collector current and collector voltage. Okay, can you please tell me, you have done with the theoretical part of this subject, that basic electronics one, or what is the means what you have been taught till now there?
Sorry, Stephen, DC motors.
Mm-hmm. I didn't get you. Could you please repeat?
DC motors.
DC motor. Okay, so in the basic electronics theory, you do not have this transistor and diode one.
No, sir. It was only basic circuits and then AC circuits
Mm-hmm.
and then simple DC motors.
Okay. So DC motor, okay. The operation of DC motor you were studying right now. So these transistors
Yes,
are
sir.
also not there. Means still, even though you are in EC one, so you people do not have.
No,
Okay.
sir.
Okay. I am not familiar with that theoretical one. Means theory syllabus. Anyway, so for this case, our IB we can consider as a 20. Means it was 20 point something. So let's consider that value as a 20. We just want to have some difference if there is any. We just want to initially we are trying to change. We are trying to have input characteristics, but VC was that output. So by changing the output voltage, we cannot change the input one. But now in this case, now let's check whether we can have this change in input. If we are trying to change in input one, we can have a output changes or not. Okay, now let's have another set of data, then only we can conclude from there. Let's clear it. No, sorry, it should be 30 then 40. No, this is 32, 31 then 30.47. Okay, 30.47. Let's take this value. So for this one, okay, then also for this set of data, we'll have this data, means variation. Will vary the voltage across the collector emitter junction, and we'll note that output current, means that collector current. Okay. So if you have not read all these things, then I was thinking that you know all this the basic of this transistor and diode. That is why you were doing this lab. So that I have considered, and so that is why repetitively I am telling that I think you people know this, know that. Okay, I was not aware of that one. I'm sorry for that. Okay, from tomorrow or today, means now onwards, I can understand that. I have to tell you little bit theory of that one. Then it will be very easier for you people to grasp it. Because lab is for explore in more rigorous way that you have not studied in experiment theory. Okay, so now let's have a data for another set. I think that will be final set. Clear. 40. Okay, no, make it maximum. Or something 174 microamps. No, that will be not the good case. So let's have some 100 to 100 micro. Okay. For the IV value of 100 micro, 100 microampere, whatever current we are having. Let's have this 100. Okay, consider this value as 100. Okay, 101.2 microamps IV value. For that one, we will like to have that same set of data for output characteristics. And so we will vary that voltage across collector and emitter. Then we will note down what will be the value for collector current. Then we will plot together. Okay, so we have the data. Very good. Now I should share that screen. This graphing window is visible, right?
Sir.
Okay, so this one is for IB equals to 100 micro. So we will plot this together. So till now also you want to go with that one, that there will be no changes, or you want to change it? Okay, we have this. Yeah, please tell me. So we can see some. Can we see some changes in the curve, or same curve we will have? We can see. Okay, through chat someone is telling. Oh, okay. Rajesh. Yes, no changes. Okay, Rajesh told me no changes. So all of you are with Rajesh, or okay, someone also, another one is telling change. Jitendra is telling changes. Okay, good. What kind of changes you are expecting, Jitendra? Okay, let's plot it. Then we can have, or we can just have discussion on that one. Oh, what is this? VCE only? Which curve it was? Oh, I think some mistake is there. Which one is only VCE?
E section, sir.
Okay, but it should not be in that way. It will be 20. IB 20 will be there. Oh, sorry. Yes. It was my mistake. Yeah, I should convert it. Again, this is, one second, this is x1, y1, x2, y2, x3, y3. This is x4, y4. Yeah, nice. Now plot it. Yeah. Good. So now you can see, this is the beauty that you, yeah, it will be better if we have another data, means another set of data in between 100 and 30 microampere in case of base current. But you can see in case of base current from 10 microampere, 20 microampere and 30 microampere, and this is for 100 microamps. So basically you can see there is a change. The nature is same, but the graph is shifting upwards. So this is very important. This is one of the crucial characteristics for transistor output characteristics in case of common emitter mode. Remember that one. That is why we have a plot of output current as collector current and output voltage as VCE, collected to emitter voltage. Obviously that is in volt and this is in milliamps. So that is why there will be changes, and depending on that, you can say there will be three operating region. That is, one is cutoff region, that is below this IB value there will be almost zero current, or you can say no current. So that is the cutoff region below the minimum value of IB, through for which we can have this kind of nature, and below that there will be no current. So that is cutoff region, and this one is you can say saturation region. Okay, and this, for this one, or for this nonlinear increasing one, you can say active region. So that is the case when you are changing the voltage across these transistors, means two different junction. Then you can have that different characteristics. When you change the voltage across the base emitter junction, basically you are changing the IB current. So due to that only, and this will follow that one small thing I told you in case of that. Let me that when this will be in in which region, that if the base emitter junction is in forward bias, yes, this one. When the base collector junction is reverse bias and base emitter is in reverse bias, so then they will be in cutoff. So in this case, in VLAB, we have only that means fixed connection. But in multi-SIM, you can have different type of connection. Means you can directly rotate that configuration of that source. Okay. In that one, you can have that cutoff region. So in both of your junction is in reverse. Any one of them are in active, forward, then it will be in active region. Okay. And both of them are is for forward, then it will be in saturation region. So that thing we can conclude from here, means this output characteristics of this transistor. Okay. So it is very useful object, means basically, or more or less you can say transistor having so many applications, but more or less you can say it is used as a switch. So in case of switch, there are so many applications. Amplifiers are also there, and so many applications are there. Basically, it is also used as a switch, and that is why means, and also we need switching. Means our ideal requirement is that we should have a ideal switch that when I turn it on, within zero lag, it will starts flowing current. Once I turn it off, then it will stops flowing current. That should be the ideal characteristics of a diode. And the basically transistor, we moved from BJT to MOSFET or FET, you can say that field effect transistor devices, and from MOSFET to CMOS. Common means both there is PMOS and NMOS, both CMOS, and nowadays people are using FinFET. I think all of your mobile devices are made up of FinFET. So basically, those are kind of transistor only. So basically, they used means they are along with the advancement of what we are asking for, only that switching rate is so should be as high as possible, and there should be no leakage or something like that. Ideal switch we are trying. There are so many aspects you will come to know in later. So that is why this is the basic characteristics of a transistor. Output characteristics in common emitter mode. Okay, there are three different modes, means I already discussed with you. Okay, for today, now we'll go to the multi-SIM one. Then there we'll study that common emitter one, and the next lab onwards we'll study that other two modes. Okay, now let me see. Is there any query till now? If you have, then please ask me. Then we'll simulate that circuit. Anyone? Do you have any query? Please ask me. And that graph plotting one that you have asked me in the last. Am I audible to everyone? I think the connection was lost, right?
Yes, sir. Yes, sir. Now you are audible.
Okay, okay. I'm sorry. Okay. So I was telling that we have already discussed. Okay, let me share my screen. We have already discussed that we can plot it directly if we have the DC sweep mode. Here you can see, here we have interactive mode, transient mode, and AC sweep mode, and DC operation, means that operating point mode. In this online mode, it is not having that DC sweep mode. If we have a DC sweep mode, then we can directly plot this graph that we have plotted over here in that our graphic software. No, but So as it is not here, so you people have to help me to note down the data and then we'll plot it. Okay. So let me draw the circuit. So very quickly we need a transistor, means BJT. Oh, sorry, it is called. Okay. So NPN transistor, we need a NPN transistor. Good. Then what do we need? We need two resistor. One is with base and another is with that collector. Sorry, this is emitter one, and one should be with your collector. Okay. So, and this should be high, this would be low, make it as, let's say 100, and this is also low resistor, make it also 100. Okay. This should be high always, because base current should not be greater. In, as you can see that in all the simulation also we have considered it is in microamp, so base current should not be high, so that is why we have used a higher resistor over here. So now you can clearly see this is one junction or one terminal or two port. This is one of the two port of input port, and this is the output port. So emitter is in common, so that is why you can say that it is in common emitter mode. Okay, make it ground. My screen is visible to you people, right?
Yes, sir. Multi-sim.
Yeah, multi-sim one. Let me connect this. Yeah, it is grounded. Now what we have to apply, you have to apply to DC voltage, or you can say voltage source. Before that, we have to measure the current. Means so we need, okay, no issue. We can directly connect it. Okay, another source we need for this junction. Good. Now make them connect. Good. So could you please tell me which bias I am considering for both the base and collector, means base emitter and collector emitter one? In this case,
Forward by
this is in forward and this is in reverse, right? Okay. So now what do we need? We need that 1 volt voltage one we need. Do we need voltage? Yes. Our input, yes, this will be IB, and we need a voltage also at that particular point. Sorry, we need a current in this branch and we need a voltage. Okay. So now let's run it and check it. No, Sorry, you do not need this one. We need a operating frequency, sorry, operating fixed operating point. So from this one to DC opt. Okay. Now just run it and we will have to, okay. So any one of you please note down. Please note down and tell means after completion I will ask you the data. You please tell me in this fashion. We need
So the volts and
in this fashion we only need that VB voltage and IB current, and you have to we will consider for only for one set of data because we have seen there is no deviation. So that is why input characteristics will consider the VCE for one set of data. Okay. So it's just what we have to do, you have to make a two column. One is VB. Oh, my screen is not visible to you, right? Sorry. So what you have to make, you have to make this two like column like two. This one is VB and one is IB. Okay. So VB unit is in volt and IB unit is in microamps. Okay. Is it clear?
yes.
Anyone please note the data. I will tell you. Okay. And then only we'll plot this. Okay. One more thing we have to do, that we have to measure this voltage also. Yes. That, sorry, collector voltage also we have to measure. So this is not probe 3. This name will be, this name is VCE. Okay. And this one is not probe 2. This is base current. This will be IB, or and this one is VBE, base emitter voltage. Okay. So this, okay, now just change the voltage. Let's say we have considered it as a 1 volt. Okay, 500. Okay. So for who is who will take this data? Please, anyone note
Sir, I will,
the data.
sir,
Okay.
sir, I will know.
Okay, please note down. Okay, so you just note it down that your VCE value is 1 volt. 1 volt? No, we have applied 1 volt. Let's see. Yeah, I'll tell you. Okay, so our VCE is approximately 0.689 volt. Okay, then increase. Okay, I'm increasing the value. Then only it will be easier to have a good data. Okay, now let's run it. VCE is 2.1359 volt. Please note it down. And so that should be constant. That we are not going to change it. Now we are going to change the value of this VB value. Okay, sorry, we should change it accordingly. Oh, sorry. Okay, from 500 millivolt we can start. Okay. Okay, that is in picoampere. Okay, then I think we have to increase it. I'm changing the value to, let's say, 1 volt. Actually, we have used that resistor, big resistor is there. That is why the input voltage across, means VB junction voltage is less with respect to this applied voltage. So in the VLAB, they were directly connected, but here we have connected through a resistor. That is why we are having some drop. Okay, I think now you will have, yes. So now you can note it down. Your VB value is 981 millivolt, means 0.98 volt, and IB is 18.86 microampere. Okay, noted.
Yes.
Let's can we have, okay, no, let's increase the voltage. Let's say it is 1.25 volt. No, if the DC sweep option will work, then it will be very easy for us to, I don't know why it is not in there in online option. Okay, please note down another value. The VB is 1.21 and IB is 39.65.
Okay.
Okay, now let's change the value. Let's say it is 2 volt. Now run it. Okay, so VB is 1.895 volt and your IB is 100.95 microamps.
Yes.
Okay, now just have some higher voltage. Let's check it for 4 volt only. For 4 volt, now check it. Yeah, for 4 volt, the VB is 2.86 and the IB is 1.13 milliamps. It should not be, means in practice, IB should be in microamps. Max to max in smaller value of milliamps, but it should not be in higher value of milliamps in that. Okay, so you have noted?
Yes, sir. Noted.
Yeah. Now you please tell me the value. I will plot them. Now the plotting option is visible to you, right? Means plotting screen is
Yes,
visible to
yes,
you.
sir. Yes, sir.
Yeah. Please tell me this in this fashion, VB and
VB and IB.
VB and IB, and please also told me the value of VCE once. VCE is equals to how many volts?
3.811.
3.811 volts. Okay, VCE value. Good. Now tell me the VB value. One by one.
0.98
0.99
volts and IB value 18.86
18.86. Okay.
microamperes.
Yeah, it is. Units are given microamps. Yeah.
Next 1.2103.
1.21. Sorry, 1.21.
03.
Okay,
And
let's
here
consider this 1.30.
39.65. 39, sir.
Okay, 39.65. Okay, next
1.89.
1.89.
104.95.
104.5.
95.
95. Okay. Okay, next
2.8. 2.86.
2.86.
1.131 milliamperes.
1.131. Sorry, 131 milliamps.
131
Okay.
milliamperes.
Yeah. Oh, sorry,
That
milliamps.
that
Means
yes,
it will be, yes.
1131.
Yeah.
That's it.
Okay. So now we can plot it and we can see the nature, whether it is similar to that of that VLAB one or not. Yeah. As we are having less data, so that is why it is in this way. Otherwise, you can see that it is having that exponential increasing one, right? Yeah. So exponentially increasing curve. Okay. So this is input characteristics for common emitter mode, and the current is IB in microampere and voltage in VVE. Sorry, voltage in that voltage across base emitter junction, which is in volt unit. Okay. Okay. Now let's for this one, let's have that that VC and IC. Okay. For now, in this case, now we have to take another different value. Means for IB equals to in microamps, we'll consider different value. Okay, so not in function, in comment, this one. Okay, write it down. IB equals to, let's have some 10 microamps. Okay. Now go to that our simulator. What do we need? We need this two value. Means just for same circuit, we have to change replace that measurement device. We need VCE and IC. Okay, IC. Since we need this one. Okay, this is IC, but it is in opposite direction that you have applied. Yes, yeah. So it is IC, and what do we need? VC. Okay, this one we do not need. Let's remove it. Oh, okay, it is not required. Let it. Okay, let's remove it. Then we need VC. Okay, so okay, one more thing we need that IB. So instead of that, we have to use another current source over here, and this is IB. Okay, so for a particular value of IB, we'll have to take some data for collector current, which is in opposite direction. As you can see in this case, IB was in this direction, IC is in this direction. So that we have to take several set of data for different IB value. Now for this one, let me check what is the IB value. Okay, so we can have a 2 volt as a output. Sorry, 2 volt as a base emitter junction. So this is 2 volt. Now let me check what is the IB value. Okay, it is higher quite. Let me increase the resistor, then we can have 10 kilo. Then we'll have less current, I think, in 58 micro. Again, 100K. Yeah. 11 micro. Good. So who is writing? Please note down for this set of data. IB is constant. We are keeping IB as a constant in 11.10 or 11 microamps.
Okay.
Now what we are going to do, we are going to change this voltage. Then what will happen, this VC will change, and as a result our IC will change. So depending on that, we have to note these two value, VC and IC in this fashion. Okay. Let's start with 400 millivolts. If this value will automatically updated, then we don't have to. Okay, no issue. So note down the first value, that VC is 295 millivolt, or else you can write it in 0.29 volt, 295 volt. And our current IC is in 1 milliampere. Okay. Noted?
Yes, sir. Yes, sir.
Okay. Please respond once, then it will be very easier for us to communicate. Okay, now let's 400 millivolt to 800 millivolts. Okay. For 800 millivolts, check the value. Please note down another set of data, that VC equals to 0.68.
Noted.
Yeah, good. Then let's change the value to 1 volt. Then we'll have, okay, IC is not changing in that much. Okay, so VC is now 0.88.
Noted, sir.
Okay, good. Now let's change the value in this fashion. 1 volt, let's say 3 volt. Okay, 2 volt. Or 2 volt, what is the VC? VC value is 1.889. Again, the IC is 11. Okay, noted. You have? Okay.
Yes,
Good.
sir. Yes.
Now please change it to 4 volt. Let's see. 4 volt. Okay, in 4. So 3.88 volt, and current is constant 1.11.
Noted, sir.
Okay. Now I think current is saturated. Let's have some 8 volt data. No. Okay, 8 volt. Yeah, 8 volt. Yeah, 7.889 volt, and current is 1.1109. So current is constant almost. Okay. So for this set of data you have taken, right? I'll first let me do the experiment. Then you told me. Then I'll one by one note it down. Now increase this one for 11 microamps instead of 11 microamps. So we'll have, change it to 5 volt. What would be the current? That will be, yes, 40 microamps, 43. Yeah, please note down this value. Means IB value. Means for this IB value, we will have another set of data. IB value is 43.93 microamps. Okay.
Yes, sir. Noted.
Okay. Now what we will see, or what we will do, that we will change this value to 100 milli. That's 0.8 volt. Okay, let's. And we have. Okay, let's check it. What will be the current? Then depending on that, we will change it. No, let's another decrease it. 80 millivolts. Okay, please note down that VC is equals to 64 millivolt and IC equals to 157 microampere.
Noted.
Okay. You will have lack of time, so you have to hurry up. 80, then 100 millivolt. No. 1 volt. Yeah, please note it down. 0.593 volt and current is in 4.06 milliamps.
Noted.
Okay, good. Now, okay, initially it was 80 millivolt, right? First data it was 80 millivolt, and then we have considered 1 volt, right? In
So
between
initially
initial data for this set 80 millivolt.
64.
Yeah,
64.
millivolt, right?
Yes, sir, milli.
And now we are having 593. So huge gap is there. Okay, let me have some another data. At least 500 millivolt. Okay. Yeah, this one is also good. Yeah, please note it down and tell me, means
Noted.
insert it above the last value. Okay, as because the voltage is less. Did you get that?
So,
Okay.
so please repeat what you said.
Yeah, actually for this data, the voltage is 0.316 volt. Okay, and the,
Yes,
before the data, before this I told you that means that you have noted it is around 0.8 volt, right?
it's a 0.06 volt and
Yeah. Okay.
0.5.
Okay. You just note it down. Once you will tell me, then I will tell you what. Okay. After that, we will have 2 volt. Okay, 2 volt, something like that. Yeah. So voltage is 1.66 volt and current is 4.393. 393. Yes, 393 milliamps.
Noted. Yes.
Okay. Next, 5 volt. Yeah, for 5 volt, it is current is saturated. Means voltage is 4.71, but the current is, I think, almost similar, 4.393.
Yes, sir.
Yeah. Let's have some another data up to 10 volt. Initially, what was the last value for the previous set of data?
7.89.
Okay. Yeah. Please note down these values, 7.96, and the current is saturated.
Noted. Noted.
4.393. Okay. So this one was for IB 43 microamps. Initially it was 11, now it is 43. So in between it will be better if we have 100 microampere. Then we can easily, okay, or else to have 100 microamps, we can decrease this. Yeah, it is 238. Okay, let's change it to 100.
Sir, are you taking more, sir?
Sorry?
Are you considering another set?
Yeah, we are considering another set. It is 100 microampere value. Yeah, we are running out of time. Please hurry up this time. So 100 microamps is the IB value, and IC value we are going to change. Do you have any another class after this lab? Do you people do you have any class after this lab?
No, sir.
Then anyway, I will try to compile within 4. Okay, so please note down this value. VC is 0.328 volt and current is 2.3653 milliampere. Noted?
Noted.
Okay, good. Now make it 1 volt, and actually the DC sweep option is not working. That is why we have to take in this way. Okay, please note down this setup data. 0.55 and the current is 4.437. Noted?
Noted.
Okay, good. Now let's change the voltage to some sort of 2 volt. Okay, it is voltage is 1.21 and the current is 9.890.
Noted.
Good. Voltage is 2.596 and the current is 10.031 milliamps.
Noted.
Now the voltage is 4.846, current is saturated 10.031.
Noted.
And for this set of data, okay, voltage is 8.09 and the current is 10.31
Noted.
milliamps. Okay. Now you quickly tell me. Okay, no, not the screen. Here. Yes. One second.
Sir, all IC values are million.
Yeah. One second.
IC values are million.
Yeah. IB value are in milli and IC value, sorry, micro, and IC value is in milli, right?
Million. Yes.
So this is in milliamps and this is in voltage. VC value is in volt, right? Okay. So
Yes,
you
sir.
quickly tell me for IB initial set of data was 11 microamps, right?
11.1.
Okay, consider it as almost 11. Then next one,
43.9.
43.9 means 44.
Next 100.
100. Okay, good. And this will be similar for all these case. Okay. And this 3 will be, sorry, this 3 will be our x-axis. Okay, please tell me for 11.1.
0.29.
0.29.
1.04.
1.04.
Yes, sir.
Okay. Milliamps and
0.6.
voltage. Okay, 0.6.
68, sir. I'm
68.
saying after means 2 digits after this.
Oh, yeah. No
1
issue.
point
1.1.
1.11.
Good. Next.
0.88.
Okay.
1.11.
1.11. Okay.
1.88.
1.88.
Yes, sir.
Okay.
1.11.
Okay.
3.88.
Mm-hmm.
1.11.
Okay, it is almost saturated. Oh, sorry.
Yes, sir. 7.8.
7.8. It is 1.11.
1.1.
Yeah. For next set of
Second
data.
set.
Yeah.
0.06.
0.06.
Yes, sir. Means 64 million
Okay.
millivolt. This is 0.15.
0.1. Okay.
15, sir. Okay. 0.59.
0.59.
4 amperes.
4 milliamps.
4 Yes, sir. 4.06 milliamps.
4.06 milliamps. Oh, sorry. 4.06 milliamps. Yeah. Please, next value.
0.31.
0. Yeah, okay.
1.98.
98.
98, sir. 1.66.
1 second. 1 second. One second, please. Yeah, please. 1 point.
66.
Yeah.
4.39.
4.39. Okay.
4.71.
4.71.
4.39.
Okay, it is saturated. Next step.
7.96. 7.96.
Yeah.
4.39.
Yeah. Quickly, the next set of data.
Yes, sir. 0.32.
0.32.
2.36.
2.36. Okay.
0.55.
0.55.
4.43.
4.43.
1.21.
1.21.
9.89.
9.89.
2.59.
2.59.
10.03.
10.03. Okay.
4.84.
4.84.
10.03.
Okay. Last data.
8.
7.
Yes, sir.
8.
8.09.
8.09. 10.03.
10.03.
Okay, good. Now let's plot this data very quickly. Now we can observe the same nature, right? Let's make them smooth a little bit. Oh, sorry. So you can see, so this is the output characteristics of a NPN transistor. Okay. And for this is the IC means the collector current in milliamps as a function of collector emitter voltage, and for different set of base current. As the base current is increasing, then the nature is same, but it is shifted upwards. Means we will have a higher saturation current. Means at saturation current initially it was around 1, and now it is around 4, and for this case it is around 10. So as we increase the base current, saturation current is increasing. Okay. So is it clear, or do you have any doubt? Please ask. We are end of our today's lab almost. I can, yeah. Do you have any query? Anyone? Okay. Then thank you for attending this lab. See you in the next lab.
Thank you, sir.